So, ladies and gentlemen, let us talk about the implementation of a little explosion system today. What is the assumption here? So we assume that there's a bullet and a spaceship, both move through space with a certain velocity. They may get acceleration, but that's not so much of interest for us. We just assume that there's a certain time point when someone tells us, okay, now at this time the bullet hits the ship, and in addition someone tells us where the point of collision is, meaning at which point does the bullet hit the spaceship, and then at this collision point we want to create a little explosion effect. The particles or the explosion effect is then realized in a couple of steps. So as we will see, and we will describe all these steps in more detail later on. So what do we do? In the first step, we create a set of particles right at the collision point, the so-called seed point. But then we scatter the particles randomly around the collision point, and in order to give the whole thing a little bit of a realistic random touch, and so that all particles are not starting at exactly the same point, but they are just slightly scattered around that initial seed point. Then we sort the particles with respect to the view plane. We have to do this because what we do later is we represent every particle by a quadrilateral, and the color contribution of each quadrilateral is rendered or is blended with the color contributions of whatever has been rendered before. And we know in order to blend different contributions properly, we need to render the objects in sorted order and then use an appropriate blending equation. That's what we have discussed in the chapter on blending. We then represent each particle by a small textured quadrilateral. We call this a billboard, and then these small textured quadrilaterals are rendered, but before we can render them, they first have to be aligned so that they are parallel to the view plane. We will see later on why this alignment has to be done. Once this alignment has to be done, we can then render the particle billboards in the sorted order, which we have determined in step 3. We then blend the particles into the color buffer. We then simulate the particles' movement, because we want that the explosion, so to say, is spawned from the seed point and now grows into space, meaning that we have to simulate that explosion behavior by moving the particles accordingly. And then we repeat with step 3. Now we are going back here until enough steps have been performed, or someone tells us that the explosion should now die and should not be visible anymore. So we will not talk about how to find the collision point in an efficient way. Collision detection algorithms will be discussed in the lecture Game Physics by Niels Thierry. For now, maybe just a hint to a very simple approach in order to obtain a very efficient collision detection algorithm for the particular situation we consider here, where a particle and a spaceship should be collided with each other. So let us assume we have some object here, so the spaceship or whatever other object we have, and let us assume the bullet is represented just as a point projectile. And so now what we want to do is we want to now know at which point does the bullet intersects the object. And therefore what we can do is we can always say, okay, the current position of the bullet is connected to the previous position of the bullet via a line segment, and then we just test every triangle of the object against the line segment, and we check for an intersection between the line segment and that triangle. Of course, that would be computationally very expensive, because if the object has thousands or even tens or hundreds of thousands of triangles, then we need to test the line segment against every triangle. So instead, what we typically do is we first of all compute what we call a bounding volume representation, or in this case, in the 2D case, a bounding square representation. That is a bounding square that as tightly as possible covers all of the vertices of the object. That can easily be computed if we assume, for instance, that this is here the x coordinate axis and the y coordinate axis. Then this bounding square can simply be computed by looping over all the vertices of the object and determining the minimum x and the maximum x coordinate of all the vertices, and the minimum y and the maximum y coordinate of all the vertices. And this then gives us the lower left corner of that enclosing quadrilateral and the upper right corner of the enclosing quadrilateral, meaning that now the quadrilateral is given. And then we can simply do, in every time step, we just take the current particle or the current bullet position, connect it to the previous one to define the line segment, and then we can simply intersect that line segment against all, in 2D, the 4 edges of the quadrilateral, or in 3D, this would then of course be a bounding cube, with that going into the display, so to say, and then we would intersect the line segment with each of the 6 faces of the bounding cube. That is something you, for instance, could also do if you take part in the practical and you need to come up with an efficient solution to find the collision point where the bullet intersects the spaceship. It is clear now that this approach here does not give you the exact intersection point, because it always gives you an intersection point between the line segment and the enclosing bounding box. But if this bounding box is tight, then at least you get a fairly good approximation of the collision point, and you can work with this approximation in order to create the explosion effect. Okay, so now let us look in more detail at the different steps. So first of all, we create a set of particles at the seed point in world space. So here we assume that the collision point is given in world space, so after the modeling transformation has been applied. And what we have to do here, first of all, we have to allocate enough memory to store the particles. So we store the particles in a linear array large enough to store all the n particles. And what we need to store for every particle is its previous and current position in particular, in order to form the line segment that is then intersected against the faces of the bounding volume structure. And in addition, we may want to store the current particle velocity, the acceleration that is acting, and whatever other attributes we want to store per particle. Its color, for instance, could also be stored. So now we initialize the particles so that all particles are initially located exactly at the collision point. But then we have said we want to also randomly scatter the particles around that initial collision point, and we want to randomly scatter it in a unit cube around that seed point. How do we do that from an implementation point of view? So for each particle I in our array of n particles, we now set the position, the x component of the position, to the x component of the seed point, and we add to this now a random offset, and this random offset is just computed by calling a random number generator twice and subtracting the values from each other, under the assumption that the random value generator gives us positive random values in the range between 0 and rand max, so a maximum random number that can be generated. Then it's clear that the difference here gives us values between 0 and between minus rand max and plus rand max, no? And by dividing through rand max, we now get values in the range between -1 and 1, and by multiplying with 0.5, we get now values in the range between -0.5 and 0.5, no? In the unit cube centered at the seed point position. We do this for the x, for the y, and for the z component, no, of the particle position, and this then essentially scatters the particles randomly around the seed position. In addition, we also want to give the particles an initial velocity, no? So for instance, let me draw it here. So for instance, the particle here should get this velocity, and so on. So we want to give in particular a velocity that, so to say, drives the particles away from the initial collision point. No? And how do we do this? We generate randomly perturbed particle seeds, no? And that is done in the following way. So we take the particle position, no? For particle I here, the position which we have computed before. We subtract from this the seed point. No? This gives us, so to say, the vector, the connecting vector from the seed point to the current particle position. And then we scale that vector here, no? By your scale factor. You can, of course, choose that scale factor however you want. But what we do here in particular is, no, that this scale factor also being affected by the random number generator, to essentially get velocities which randomly scatter in the direction. So meaning that we don't want to have the particles all going with the very same direction, but we just randomly perturb the direction so that they slightly vary. And we do this also here by using a random number generator again, by normalizing the random values via the division by rand max. And because we do not want to let these velocities become too small, we always we also define a min scale, and we say if that random value here is too small, then we take the min scale value so that the velocities do not become 0. Okay, so now we have essentially what we see here. So we have the particles which are now scattered around the collision point, and each of the particles has a velocity which drives the particles, so to say, away from the point of collision. Now we sort the particles with respect to the viewer. We have already said why we do that. Particles will be rendered as transparent billboards. For instance, here you have the billboards. That is the billboard for one of the particles. Here you have the billboard for another one, and so on. We will see that these billboards will be rendered as transparent textured quadrilaterals, and we want to blend their color contributions into the color buffer. Because we know that blending is not commutative, the particles have been sorted first, so that then we can render them in sorted order, and then blend them into the color buffer using the blend equation we have discussed in the lecture. And of course, that requires to sort and reorganize the buffers in every frame on the CPU, if we keep all the particle data on the CPU. We will later see that we can also do this on the GPU, but this is then a little bit more advanced. So now we need to create for each particle a billboard. We call that a billboard. Sometimes people call it a sprite. That is essentially a quadrilateral made by two triangles, as we see here. So we see here that is the particle position. Now we simply build two triangles by creating 4 vertices, and the 4 vertices are created by just going from the particle position here, and then, so to say, moving along X, moving along Y in the positive and the negative direction. That creates then the corner points, and with these corner points I then create two triangles which make up the quadrilateral. And how this can be done is here seen here. So here what we do is exactly what I have drawn here. So we we perturb the position x and position y, so the x and the y coordinates of the particle position. And how we do this, so we move from the x and y with a step height of 0.5 times the billboard size. Now the billboard size is that one here. Now that is the billboard size, and the same of course also in the other direction. So starting at the particle center, I move 0.5 times along the billboard size, that brings me to here, and 0.5 times along the billboard size along the y direction, that brings me here. And if I do this simultaneously, now making a step with minus 0.5 and minus 0.5, then I obtain the corner point here, the bottom left vertex. If I do it here by going plus 0.5 times the billboard size and minus 0.5 times the billboard size, I obtain the bottom right, the green corner point. And if I go minus along x and plus along y, I get the red one, and I get, if I go plus along x and plus along y, I get the point here, which we have not encoded here in the pseudocode. Okay, this is how we actually create the two triangles making up the billboard for each of the particles. So, and the z position, so to say, remains constant. So, and now you can imagine what we have here. We have a left-handed coordinate system. So the z-axis, so to say, is going into the display, axis going to the right, and y is going upward. Okay, now we have to be careful because the code on the previous slide assumes the view plane being the xy plane and looking along z. Now that is a situation which we have here. So here we have one of the billboards. And now if we assume that we are looking along z and x is going to the right and y is going upward, then we see the way how we initialize the billboard, or how we initialize the corner point locations of the billboard, is so that these billboards are now aligned with the xy plane, which is the current view plane when looking along the z-axis. However, if I now look from a different orientation, under a different orientation onto the billboards, then I want to have the billboards oriented as I see it here on the right hand side. So I always want to have the billboards oriented parallel to the current view plane, because if not, what would happen if, for instance, I'm now looking from here onto the scene, then it's clear if the billboards are in this initial orientation, I don't see them at all, or I don't see them, or I only see them as single lines, but not as an aerial element anymore. Therefore, what I need to do here, I have to ensure that no matter from where I'm looking at the billboards, they should always be oriented in such a way that they are parallel to the current view plane. And this means that in every frame, whenever the view direction changes, I need to reorient the billboards accordingly. So now how can this be done? Well, in a very simple way. So in order to orient the billboard in world space, so that is parallel to the view plane, what we need to know what is the current camera coordinate system. Because we have learned what we essentially do if we want to render an object. We have to define the camera coordinate system, which is comprised of the camera view direction and the camera up vector and the camera right vector. These R, U, and D vectors. which we have here, the right vector, the up vector, and the d, the direction vector, the viewing direction vector. And we have said that the viewing transformation is essentially the transformation that is applied to all the geometry in the scene, so that the same image is created as if from the default camera, which is positioned at the center of at the origin of the coordinate system and looking along the positive z-axis, so that the same image is now created using this default camera position, as if the camera has been positioned and oriented in the way that the right, up, and d vectors have been specified. No? So yeah, look into the slides where we essentially described the meaning of the viewing transformation, and then you see immediately that there we first build the r and the u and the d vectors, and then we build a matrix comprised of these three vectors, which has just in the columns, in the first column the r vector, in the second column the u vector, and in the third column the d vector. And then we said that we need to use the inverse of that transformation matrix, which is then the view matrix, and which is then applied to all of the geometry. And by doing this, we could then create the image from the default camera, which is fixed at the origin of the coordinate system and looking along the positive z direction. Now, knowing that this viewing matrix now essentially contains the inverse matrix, which is comprised of the r, u, and d vectors, what we can do is we just take the view matrix, we compute the inverse of that view matrix, and this then gives us a matrix which has in the first, second, and third column the r, u, and d vectors. And we can just read them out. And then what we have obtained then is these three vectors r, u, and the lookup vector d, or the view direction vector d. And now in order to align our billboards, we just take the up vector u and the right vector r, and we replace this up vector u and the right vector r with the, so to say, vectors which we have used here in order to reposition or get the corner point of the quadrilaterals from the particle center position. Because here we have said that we take the corner, the center point of the particle, and then we move a step of 1/2 along the x, and then we move a step of 1/2 along the y, or into the negative direction. Then this then brings us to the corner points. Okay, now we have to do the very same, but we have to use the up and the right vector, meaning that we take the center point of the particle, and then we move 1/2 of the billboard size along the right vector, and 1/2 of the billboard side along the up vector, or into the negative directions, and this then gives us the corner points of the quadrilateral, or the billboard. And this then gives us an orientation of that quadrilateral, so that the billboard is parallel to the current view plane, to the current RU plane, right up plane. And this is exactly what we want to have. So keep in mind, and if you do not immediately understand it from what is given here on that slide, please look back onto the slide where we introduced the viewing matrix, and then you will see immediately that we used there the right, the up, and the d vectors in order to form that matrix. And you will see there in particular that we build the matrix just by plugging R, U, and D in the first, second, and third column of this matrix, and then use the inverse of that matrix, meaning that the view matrix is essentially the inverse of the matrix which we need here in order to look up R, U, and D. And therefore we first have to compute the inverse of the view matrix here, and then we can just directly read out the first, second, and third column RUD from that matrix and use them in order to define the directions along which now the particle center point, so to say, is translated in order to define the billboard edge corners. Yeah, that is what you have to do in every frame. No? So in every frame, no, you have to reorient or realign the billboards in a way we show it here. So now you render the particles using view space aligned quads, and in particular, no, you texture the quads in a very specific way. What you use, or the textures you use, they can look, for instance, like what you see here on the left-hand side. This is just a set of pre-computed textures which look a little bit like fog, smoke, yeah, fire, whatever you want to encode here. They should look a little random-like, no? To give the whole thing a realistic look, because very often, no, if you look at explosions, for instance, or if you look at clouds, if you look at fog or smog, no, then there's some randomness in these structures, meaning that now the textures you map onto the quadrilaterals, which you render for each of the particles, should also kind of mimic that natural random look. Yeah, and here, for instance, no, we have just essentially four different textures, no? So they're just slightly perturbed because you don't want to use the very same texture for each of the billboards, no? But you just want to randomly select one of the four, in this case here, possible alternatives. Now you map these textures onto the billboard, no? And then you just render the texture mapped billboards and blend their contributions together. Yeah, what you can also do is, for instance, no, instead of rendering the billboards so that the billboard axes are aligned with the, so to say, with the R and the U vector, no, of the view space, no, you could also orient the billboards a little bit, no, or you could map the texture slightly rotated on the billboards, just to give the whole thing an even more natural and irregular random touch. So now you render the particles using these view space aligned textured quads, and in addition, no, you now interpret the quads as transparent quads, and you build all billboard contributions together. And that is then what you see here in this image. That is essentially what you see here, but here we didn't use blending, or sorry, we didn't use transparency. Now all the textured quads are treated as opaque quadrilaterals. And now we give them some transparency, for instance, transparency corresponding to the brightness of the texture values, or maybe you have a transparency map which you have pre-computed, which you use no matter what. No? Now, once you have the transparency, you can then blend the contribution of these transparent quads together, and this then gives the appearance which we see here in this image. And I think now you see nicely that even though the whole thing is only comprised of a set of two-dimensional quadrilaterals which are blended together, you get a nice impression of something that is three-dimensional. You have the feeling that this is a three-dimensional volumetric structure, like a cloud or like a fog structure. And that is just only been achieved by using two-dimensional billboards and blending them together. Yeah, in order to blend them, we turn on alpha blending in the shader and set the blending equation appropriately. Now we have talked about the blending equation. The blending equation essentially tells us how to mix the color of the incoming fragments, the so-called sources, with the pixels already in the color buffer, the so-called destination. And here's again the blend equation we use in that particular application, and that is essentially the blend equation we introduced in the chapter on blending already. You first of all enable blending so that blending is performed. And then you set for the source and the destination color the blend factors. For the source, for the incoming fragment, you say it should be first multiplied with its own alpha, and you say the destination should be multiplied with 1 minus the alpha of the source fragment, and then you specify that these two weighted color contributions should now be added together. And this is then the blend equation which we use here. Yeah, then we are almost done. The final thing we have to do is, once all the particles have been rendered, we want to simulate the particle movement. And the particle movement here is done by what we call an implicit Euler integration step. So in such an implicit Euler integration step, well, is very simple. So all you do is just the following. You assume that you have the current particle position stored for each particle. You also assume that you have the current particle velocity, which is stored for each particle. And you also assume that for each particle you have the currently acting acceleration, like for instance the gravity. That can be a constant that is the same for all the particles, like the gravitation, but it could also be a wind field that acts on every particle to accelerate it into a certain direction with a certain speed, so to say. Okay, and what you now do is, so given the old velocity, you first of all update the velocity by using the acting acceleration. So we know that acceleration multiplied with time is velocity, meaning that what you do here, you add to the current velocity the velocity that comes in addition because the acceleration acts by multiplying the acceleration with the delta t here, with a time step. And then you take that new velocity which has been computed here in order to change the position of the particle. You say the new position of the particle is just the old position of the particle plus the gain in position, or let's say the change in position that comes from the velocity of the particle, and that is just the new velocity that has been updated before times the time step over which you want to simulate the movement. This gives you then two new values, the new velocity and the new position of the particle, and yeah, you need to restore them then as the new positions, and then you can simply define the line segment connecting the last particle position to the new particle position, and then intersect that line segment with all of the faces of the bounding volume structure. Yeah, and this kind of, we call this a numerical particle integration. We essentially integrate that particle here over time, and at each time step by updating the velocity given the currently acting acceleration, and then updating the position given the current velocity, and this then moves every particle over time through space. Okay, we can also use different particle emitters and alter the billboard geometry and appearance over time. That is, for instance, what you see here. Here you see for one single particle, which is spawned right at the collision point here at the center of that yellow cube, which is, so to say, the particle or sprite or billboard emitter. And what you see here, for instance, that in addition to what we have discussed before, we can of course also enlarge the billboard over time, meaning that at the beginning, if you have many particles which are very close together, you get a quite dense volumetric effect. But then, of course, because the particles are, so to say, because the particles are spawned away from that collision center here, then of course with increasing time, when the particles move further away from that particle center, and you would always use very tiny billboards, then of course you would not get a very dense volumetric appearance anymore. And therefore what you can do, and this is illustrated here by the blue quadrilaterals by the blue billboards, you can just continually enlarge these billboards over time, so that with increasing time or increasing distance from the collision center point, these particle quadrilaterals become larger and larger, fill more and more space, and always appear like a dense volumetric structure. Yeah, and then you see the final results in this way. It could look, if you do it as we have described it. And let me just here quote a sentence or some sentences from GameDev.net, where they said, okay, the sprites or the billboards, they grow almost instantly at first. They become larger and larger upon seated at the collision point, and then over time they drift apart with a slow rotation. The gravity setting on this emitter should be negative value but close to zero, so the smoke will slowly rise over time instead of falling, meaning that it should not so that all the particles are immediately, so to say, driven down to the ground due to gravity, but you want to keep them as a kind of with only a slight acceleration down to the ground, so that they keep more or less in that spherical region here around the collision center point. The color should start out bright yellow, orange, and change to black quickly as the flame turns to smoke. That is something so that right after the explosion, we have this very bright yellow-orange spot, and then over time, so to say, the explosion cools down, and the particle color then smoothly changes down to black, and at the very end, the particle should become completely invisible, so to say. The explosion is not active anymore. Yeah, a little bit of implementation details here. So the discussed technique creates billboard geometry on the CPU, as I have said this. But of course, you could also create the billboard geometry directly on the GPU during rendering using the geometry shader. So when we introduced the rasterization-based rendering pipeline, we said that there is a shader stage, the geometry shader stage, which allows you to create additional geometry or additional vertices. And this is exactly what we want here, because for every particle, which is represented initially by a single point in world space, we now want to create two triangles aligned parallel to the current image plane. And that is something we can now easily do in the geometry shader. The geometry shader gets as input just one single particle, and then spawns or creates that these two triangles, orients the triangles properly as we have described them, and then pushes the resulting geometry further into the upcoming stages of the pipeline. Yeah, the vertex shader therefore would just transform the particles via the view matrix. The geometry shader then gets as input the current particle coordinate in camera space, and then the GS, the geometry shader, simply spawns the billboard geometry and now aligns the edges with the appropriate axis. So if we are here in view space or in camera space already, then we just use the right and the up vector of the camera space, which have been issued as shader parameters that can be used. We could even perform the particle integration on the GPU, the change of the particle position and velocities over time. Therefore, we would just store the particle positions in a GPU memory segment, and then in every frame, we would just use the stored values in order to compute updated quantities, and we would simply rewrite these quantities then into another GPU memory resource, so that it then can be used in the particle explosion system. Yeah, and we could even perform the particle sorting on the GPU. So there's libraries available on the GPU which you could use for this purpose. Or you could do this by hand, by just storing the particle position in the buffer, then just using shaders in order to compute the distance of all the particles to the current view plane. and then you could just implement sorting algorithms on the GPU. Whatever sorting algorithm you have in mind, the bubble sort, for instance. There's also more or sorting algorithms which can be parallelized in a better way on the GPU. For instance, if you're interested, this is for the bitonic sort algorithm. There's also, as I said, libraries which already implement bitonic sorting for particles on the GPU, especially if you use the so-called CUDA compute API on NVIDIA graphics cards. Yeah, but this is just for the sake of completeness. No, we don't want to go into the details of these on GPU computations. Just if you're interested to do that, it should be clear that all these operations in principle do not need to be performed on the CPU exclusively, but all of them can really be done on the GPU, so that you can exploit the massive parallelism which is available on these architectures.